Welcome to the Metabolic Maestro, where we help you orchestrate your metabolism one note at a time. This is episode 2, ATP, Why Energy is Fragile and How the Body Protects It. I'm Kathleen, a synthesized voice Bob has chosen to host his podcast. Welcome back to the Metabolic Orchestra series. In the last episode, we talked about electricity, sodium, potassium, and magnesium. Today, we're going deeper. We're talking about adenosine triphosphate ATP, a molecule so important that life stops without it. And yet ATP is fragile. Part 1. What is ATP? ATP stands for adenosine triphosphate. It has 3 parts: a nitrogen base, adenine, a sugar, ribose, and 3 phosphate groups. Those 3 phosphates are crammed together, their negative charges repelling each other like magnets forced into a box. This tension stores enormous energy. When one phosphate breaks off, that tension releases like a spring uncoiling, and that energy becomes available to power muscle contraction, nerve signaling, protein synthesis, DNA repair, ion pumps, and detoxification enzymes. ATP is not energy storage. It is energy currency. Part 2. The ATP problem. Your body holds only a few seconds worth of ATP, not minutes. Seconds. If ATP production stopped right now, consciousness would fade almost immediately. So the body must constantly regenerate ATP thousands of times per second. This is why mitochondria matter. I don't want to lose you here, but this is one of those places where a little chemistry really pays off. Once you understand where these molecules come from, the health benefits of certain foods and supplements start to make a lot more sense, and it will also help you understand what I'm about to tell you about glycolysis. There's a molecule called NAD, which stands for nicotinamide adenine dinucleotide. When it's carrying high-energy electrons, we call it NAD. When it drops off those electrons and is ready to be used again, it's called NAD+. What's interesting is that the name itself tells us a lot. Nicotinamide comes from niacin, also known as vitamin B3. Adenine is one of the same building blocks used to make ATP, DNA, and RNA, so this molecule sits right at the core of energy and life itself. And dinucleotide simply means it's made from 2 small molecular units joined together. So NAD isn't some foreign chemical. It's built from vitamins and basic biological parts your body already uses every second of the day. Think of NAD as a rechargeable battery made from vitamin B3. When it's charged, it carries energy. When it's empty, it's ready to be recharged again. This simple cycle helps power almost everything your body does. Part 3. Where does ATP come from? There are 3 main systems. 1. Glycolysis takes place in the cytoplasm, outside the mitochondria. It breaks glucose into smaller pieces to release energy without needing oxygen. This pathway is very fast, which makes it useful when energy is needed immediately. However, it extracts only a small amount of energy from glucose. When glucose is broken down through glycolysis, it produces pyruvate and NAD, the charged form of NAD. If the mitochondria can't use all of this NAD and can't recycle it back into NAD+ fast enough, NAD builds up and NAD+ runs low. Glycolysis requires NAD+ to continue, so in order to keep the process from stalling, the cell converts pyruvate into lactate. This reaction uses NAD and regenerates NAD+, allowing glycolysis to keep running. 2. Oxidative phosphorylation occurs inside the mitochondria, where nutrients are fully processed using oxygen. Electrons flow through a controlled system called the electron transport chain, building an energy gradient that is then used to produce large amounts of ATP. We'll return to this later, but remember this system. This process is highly efficient and sustainable, supplying most of the cell's energy during rest and steady activity. Because it depends on oxygen and healthy mitochondria, oxidative phosphorylation cannot respond instantly, but it delivers far more ATP over time. 3. The phosphocreatine system recycles ATP instantly and requires no oxygen, but it has a limited capacity. The phosphocreatine system doesn't make ATP, it keeps the ATP coming during sudden energy demand, buying time until glycolysis and mitochondria catch up. It might help to relate these systems to a 100-yard sprint. Phosphocreatine kicks in first immediately within the first few yards. It's your instantaneous energy source because it's already there in your muscle cells. This is what gives you that explosive start. Then glycolysis ramps up as phosphocreatine depletes around 10 to 15 seconds in. For a 100-yard sprint, glycolysis is your primary fuel for most of the distance. Oxidative phosphorylation is actually running in the background the whole time, but it's too slow to be your primary fuel during an all-out sprint. It contributes some energy, but it can't keep up with the demand of maximum intensity effort. In review, Number 1, glycolysis. It quickly releases energy without needing oxygen, but only for a few seconds. Number 2, oxidative phosphorylation. It produces large amounts of ATP, but it's slow and is the system you use most of the time. And number 3, the phosphocreatine system, which recycles ATP instantly. Today, we focus on number 3, oxidative phosphorylation, because it is often misunderstood. Part 4. Creatine, the ATP shock absorber. Creatine does not create energy. Inside cells, it is converted into phosphocreatine, ready to restore ATP. ATP contains 3 phosphates. Thus it is called adenosine triphosphate, indicating 3 phosphates. When ATP, adenosine triphosphate, is used, it loses a phosphate and becomes ADP, adenosine diphosphate. Diphosphate indicating 2 phosphates. Remember from part 1, breaking off that phosphate releases energy? Phosphocreatine then instantly donates a phosphate back to ADP, regenerating ATP. This reaction happens faster than mitochondrial oxidative phosphorylation and does not require mitochondria at all. Creatine exists to prevent energy collapse. Part 5. Where creatine comes from. Creatine comes from 2 places: dietary intake of meat and fish and internal synthesis. To make creatine, the body needs glycine, arginine, and methyl groups from S-adenosylmethionine, usually abbreviated as SAMe, a key methyl donor in the body. This process is expensive. It uses a large portion of your methylation capacity. Methylation helps regulate energy use, detoxification, neurotransmitters, and gene activity, keeping systems responsive rather than stuck in overdrive or shut down. Nutrients like glycine, choline, folate, and B vitamins help keep this system working smoothly as demands vary. Which means when dietary creatine is low, methylation demand rises in order to create more. Dietary creatine doesn't just save energy, it frees up methylation capacity for other critical tasks. Part 6. Methylation and energy. Methylation is not optional, it supports DNA repair, neurotransmitters, detoxification, and phospholipid synthesis. If methylation is overused to make creatine, other systems feel the strain. This is why creatine intake often improves mental clarity. It frees methyl groups. Part 7. Magnesium and ATP. ATP does not work alone. ATP must bind with magnesium. Without magnesium, ATP cannot release energy correctly. Magnesium stabilizes the phosphate bonds. So when magnesium is low, ATP exists but cannot function efficiently. This feels like fatigue without a clear cause. Part 8. Potassium, sodium, and ATP. ATP powers ion pumps, especially the sodium-potassium pump, which can use up to 40% of a cell's energy. Every time sodium enters a cell, you must push it back out, and every time potassium leaks out, you must pull it back in. That's why electrolyte balance isn't just a hydration issue. It's an energy issue. When hydration is poor, ion concentrations become harder to control, and the pumps burn more ATP just to maintain balance. The body uses a huge amount of energy just to keep potassium inside cells and sodium outside. This balance is essential for every cell to function properly, from muscle contraction to nerve signals. The sodium-potassium pump, powered by ATP, is constantly at work. So staying hydrated helps your cells work efficiently, your sodium-potassium pump stay happy, and your body saves energy for movement, thinking, and all the other important processes. Part 9. Oxygen is not enough. Oxygen does not guarantee ATP. You also need iron for electron transport, copper for cytochrome oxidase, CoQ10 for electron flow, B vitamins for enzymatic steps. ATP production is a team effort. Missing one of these players slows the whole system. Part 10. ATP loss feels like this. When ATP regeneration lags, people report brain fog, muscle weakness, exercise intolerance, cold sensitivity, and poor recovery. This is not laziness, it is chemistry. Part 11. Aging and ATP. With age, mitochondria become less efficient, creatine stores decline, magnesium is wasted more easily, and oxidative stress increases. The result is not sudden failure, it is gradual inefficiency. Understanding ATP allows intervention before breakdown. In closing, let's bring the orchestra back together for one final note. ATP is the fragile currency of life. We have only seconds worth at any moment, and without constant regeneration, everything stops. But the body protects this currency brilliantly through 3 interconnected systems. The lightning-fast phosphocreatine system, powered by creatine, that buys precious seconds during sudden demand. Rapid glycolysis when oxygen is scarce. And the mighty oxidative phosphorylation in the mitochondria, our steady, high-yield engine that supplies most of our energy, the one we'll explore deeply next time. Creatine isn't just a supplement, it's an emergency reserve that spares your methylation capacity for detoxification, brain chemistry, and vitality. Magnesium makes ATP usable. Electrolytes like sodium and potassium make it affordable, because maintaining their balance can consume up to 40% of your cellular energy. And none of this works without the full supporting cast: B vitamins, iron, copper, CoQ10, and oxygen working in harmony. When this system falters, you feel brain fog, weakness, cold intolerance, and slow recovery. It's not laziness or age catching up, it's chemistry asking for support. So remember, energy is not something you store and spend. It's something you must orchestrate, moment by moment. In the next episode, we'll step inside the mitochondria to meet the electron transport chain, understand why redox balance is everything, and discover practical ways to keep your metabolic orchestra playing strong. Until then, conduct your energy wisely.